A prop beam fixed at left and with a span of 6 meters carries a concentrated clockwise moment of 100 kN at the simple end. We are tasked to calculate the moment at the fixed support in kN and compute the location in meters of the maximum deflection from the free end. And we have our prop beam on the figure on the right. Since this is a fixed end support, it will resist 3 reactions, that is force vertical, let's call this AY, and force horizontal, AX, and also the moment, let's call this N, that we need to solve. And in the roller support, this will resist a force that is normal to the surface, let's call this R. And to solve this problem, you can use area moment, conjugate beam, superposition, but the best way to solve this problem, since it is asking us for the location of the maximum deflection, we will use double integration method. So cutting this section and considering the right section so that we will neglect these 3 unknown forces, we can create our moment equation based on the right section from a distance x at the roller support. So creating our moment equation, we have the 100 kN couple that is acting in the same direction as m, so this becomes negative 100 times a distance of x raised to the power of 0. And then we add this up to the moment induced by the direction r, that is equal to r times the moment arm distance of x. And then in integrating, we get our slope equation. So this becomes negative 100x plus rx squared over 2 plus the arbitrary constant c sub 1. And then integrating, we get our deflection equation that is equal to the integral of the slope equation. This is negative 100 x squared over 2, or we can say this is negative 50 x squared. And then the integral of r squared over 2, this is r x cubed over 2 times 3, that's 6, plus c sub 1 times x plus the arbitrary constant c sub 2. Now for the boundary conditions to solve for the arbitrary constant, at point 0, you can see that the deflection is equal to 0 because this is a roller support. And at the fixed support, where x is equal to 6, since this is a fixed support, the slope of the beam is 0, as well as its deflection. So using this boundaries, we can solve for the 3 unknowns. So using the deflection equation, so at x equals 0, the deflection is equal to 0. Now notice that all terms that are multiplied by 0 becomes 0. So what we are left is the arbitrary constant c sub 2 that is just equal to 0. Now we're done with using the first condition. For the second condition, at x equals 6, the slope of the beam is 0. So using the slope equation, we have 0 equal to negative 100 times 6 plus r times 6 squared over 2 plus c sub 1. Simplifying, we get 0 equal to 600, that is negative, plus r6 squared over 2, that is just equal to 18, r plus c sub 1. Rearranging, we have 16, r plus c1 equal to 600. This serves as our first equation. And for our second equation, we make use of the last condition since we're done with this. At x equals 6, the deflection of the beam is equal to 0. So using the deflection equation, we have 0 equal to negative 50 times 6 squared plus r times 6 cubed over 6 plus c sub 1 times 6 plus 0. Simplifying, we get negative 50 times 6 squared, that's equal to negative 1800 plus r times 6 cubed over 6, that is just equal to 36 r plus 6 times c sub 1. Simplifying this equation and rearranging, we have 36 r plus 6 c sub 1 equal to 1800. This serves as our second equation. So we have two equations with two unknowns. We can make use of our calculator by going to mode 5.1, solving two simultaneous equations with two unknowns. We have 18r plus 1 c sub 1 and 600, that is the constant term, and 36r plus 6 c sub 1 and 1800 constant. We get r equal to 25 kilonewtons. And the value for c sub 1, that is equal to 150. Now we can solve for the moment at the fixed support by taking submission moment at this point here equal to 0. Considering counterclockwise to be positive, we have the counterclockwise moment m minus the 100 kilonewton meter couple that would induce a clockwise moment, so it's negative, plus the moment induced by r, that is 25 kilonewton, times the moment arm distance of 6 meters, all equal to 0. Solving for the moment m at the fixed support, we get m equal to negative 50 kilonewton meter. And the negative sign here indicates that the assumed deduction for m here is incorrect. Therefore m, instead of rotating counterclockwise, it should be rotating in the clockwise direction with a value of 50 kilonewton meter. And to compute the location in meters of the maximum deflection from the fixed end, we need to first solve for the value of x based from the slope equation, because the maximum deflection, let's assume the shape of this prop beam is somehow like this. The slope of the maximum deflection, which is right here, is equal to 0. Therefore, the angle or the slope of the beam must be equal to 0, and we will utilize this equation for the slope equation to solve for the value of x from the free end. So letting theta, the slope of the beam equal to 0, equal to negative 100x plus 25 x squared over 2 plus 150, we can solve for x using our calculator. So this is a quadratic equation. We can go to mode 5.3. So based from this equation, the quadratic term has a coefficient of 25 over 2, and the linear term has a coefficient of negative 100 and a constant term of 150. The value of x for this equation is 6 and 2. So since the length of the beam here is just equal to 6 meters, based from this result, the location of the maximum deflection of the beam from the free end, that's 6 and 2 meters, which is found probably right here and at the fixed end. So there are two locations for the maximum deflection. Two locations where the slope of the beam is 0. It is at this point here at the fixed end, and at this point where x is equal to 2 meters from the free end. And the answer to this problem, the location of the maximum deflection of the beam from the fixed end that is 6 meters minus 2 equal to 4 meters. And this is the final answer to our second problem. And for the first problem, that's the moment at the fixed support that's equal to 50 kilonewton meters. And these are our final answers.